We are now starting section 7.4, which is integration of rational functions by partial fractions. So we will be given some rational functions and we will have to write it in a simpler form to in order to integrate. So note here, we have dealt with, first thing we have dealt with some rational functions already. So for example, when we have 1 over x squared plus 1, we know that that is the antiderivative of that quantity is tangent inverse x. We already know that. And if we have something else from here, like so this is tangent inverse x, we already know. And if we have 1 over x squared plus a squared, then we know that this is going to be 1 over a tangent inverse of x over a. And if you forget this, you can always do the substitution, x is equal to a tangent theta, and find the integral. And there are a bunch of other rational expressions or rational functions that we have integrated. So this time we will be looking at a certain type of functions which can be simplified and written as simpler, as a sum of simpler rational functions or rational expressions. So note here, if you look at this sum or difference of two rational quantities, this is very easy to integrate. So if you recall, the integral of something like this will be just ln of absolute value of x minus 1. And how can you do that? Make a u substitution for x minus 1, set x minus 1 equal to u, and then you integrate. And in the same way, the other piece, 1 over x plus 2 dx, so this will be ln of x plus 2. Again, by making a substitution, you should be able to do it. Now, instead of that, if you are given a rational expression of this form, that is not so easy to integrate. You can try doing substitution for the denominator, like u equals x squared plus x minus 2, but you will see that you still are not able to figure out how to do the complete problem or complete antiderivative. But if you note, these two quantities are actually same. And how can you do that? Well, if you take the common denominator here and work it out, you will see that you end up getting this. So this is something we have been doing since we learned algebra. So it has been some time since you guys have been doing it. Like if you are given two rational functions being added or subtracted, you take a common denominator and you convert it into one fraction. But now partial fractions allows us to go backwards. If we are given a fraction, single fraction, we can sometimes write it as a sum of more than one fractions which are simpler than the given fraction. And that is what the method of partial fractions is. So when we are given a rational function, so for example, something like this, and where, remember what is a rational function, where the numerator and denominator are both polynomials, then we can have two conditions, or actually we can have three conditions, but we divide them into two categories. So one is when the numerator, the degree of the numerator is less than the degree of the denominator. So that is the first case here. Then we can use the method of partial fractions to break it or write the fraction as a sum of simpler fractions, sum or difference of simpler fractions. And the second category, we combine equality sign with that. So the degree of the numerator is greater than or equal to the degree of the denominator. Then our best choice is to do the long division and write the expression what is left. And remember how we write it. So quotient plus remainder over divisor. So if you recall, if you are dividing 253 by, let's say, 5, then how would you do it? You will divide it like doing the long division. So subtract, nothing is left. So we bring down 3, so it doesn't go, we put 0. Now how can we write 253 over 5? We can write it as 50 plus 3 over 5. Normally we write it as 50 whole 3 over 5, which is actually the same thing. So in algebra, when we have algebraic expression, this is how we will write. So this is our, we call it the quotient, and this is our remainder, and this is the divisor. So the remainder we are going to call it denoted by R. The quotient we are denoting it by the S, and the Q we have the divisor. So we will be doing long division. So the first example I have chosen here is where we are going to do long division. So I'm going to erase this and show you the long division. So by the way, so how do we do it? First, let's look how the solution is obtained. So we are given this expression that x cubed plus x over x minus 1, and we have to integrate this. So we see that the degree of the numerator is bigger than the degree of the denominator, so we do long division. So I will show you the long division in a minute, but by using long division, this expression can become equal to that, where this portion is the quotient, this is the remainder, and this x minus 1 is the divisor. But now if you notice how easy it became to integrate this quantity, so you just integrate and you get your answer. So some of you may have forgotten long division because it could have been like so many years have passed since you did long division. So this is how we do long division. So we of course have the divisor outside, which is x minus 1, and then we will put the dividend. Remember, the thing which is to be divided is called dividend. So we make this sign of long division. We put the divisor here. So I'm showing you the long division of this for this example, where the dividend is x cubed plus x. Now note here, if you think about writing the expression x cubed plus x in the proper format, in the standard notation, then we have to have the terms in the descending power of the variable. So you can see we have a power missing, actually two things missing, the constant and x square term. So normally what you should do is, there are two ways. You can either leave some space for those missing, or you can write it as 0 times x squared, and then we have the x term and then plus 0, or we can just leave space. So, and not leaving space can be result in mistakes. Okay, so either leave space or put the missing term with a 0 coefficient multiplied by a 0 coefficient. So as I said, so we write it like this, or we will just not write it but leave space. So the next thing we do is we try to see what should we multiply this x with, so that when we multiply the two quantities, we end up getting this first term x cubed. So we only look at the first term of the divisor and the first term of the dividend. So what should we multiply x with so that we end up getting x cubed? And you can see that we should have multiplied by x squared. So that is what we put up there. And now we will multiply x squared by the whole divisor, and we end up getting x cubed. So x squared times x is x cubed. We will put x cubed under this x cubed term. So the similar terms should be written below, each other. And then I have to multiply x squared by -1, so which will give me negative x squared, and that is what we will be putting over here, because if we had an x squared term, that would have been here, so we put it under in its place. The next thing we do is we change the sign, or we can say we multiply by -1. So we will put negative sign like this outside, and then put a line, and now we are going to add the terms. So we have x cube, we will read it x cube minus x cube. So this will cancel. And now what is left is minus times minus x square or plus x square. So I write plus x square. And now if the next term is given, which is the next term in the descending order, then we just bring it down, which is what we have here. And now we again look at x, the first term x, this term x, and try to see what should we multiply that with so that we end up getting x squared. And we notice that we should be getting writing plus x. So now when we multiply with x, we end up getting x squared minus x. So change the sign again, negative sign outside, so x squared and x squared cancel. But now we have x plus x, so which gives us 2x. We do not have a next term given, so we cannot bring anything down. But note here, the degree of this term is the same as the degree of the divisor. So we should still divide one more time at least, because the degree of the remainder should be less than the degree of the divisor. So what should we now multiply x with so that we end up getting 2x? So that you can see we should be putting a 2 up here. So we get 2x minus 2. Change the sign, the 2x and 2x cancel, and we are left with 2. Now the degree of this 2 is less than the degree of x minus 1, so we are done with the long division. So that now we can say that our expression, which was x cube plus x over x minus 1, we can write it as the quotient, which is x squared plus x plus 2 plus the remainder over the divisor. And that's what I have here. And then we can integrate easily. So this is how we will be doing when we have long division, when the degree of the numerator is greater than the degree of the denominator. Okay, so what happens when we have the degree of the denominator is bigger than the degree of the numerator? So we have 4 different cases, but we are only going to discuss 3 of them. So the first case we discuss is when so by the way, all these cases depend on how the denominator factors. So if the first case is if the denominator has factors which are linear and distinct, like all factors are different from each other, so no repetition. So then how do we make partial fraction? So first example we are looking at is that we have to integrate 1 over x squared minus 1 dx. Now notice here again, you cannot do it by using the just direct substitution. So we factor our denominator, which can be written as x minus 1 times x plus 2 plus 1. Now we go on a side and we make partial fraction. So how do we make partial fraction? So remember, whenever you have linear factors, you will just take the a, b, c. We normally take the uppercase a, b, c as our kind of the coefficients which we have to find out. And why we are doing this, again, recall in the beginning of this example I showed you that when we have an expression like this, notice here when we write it in partial fraction, it becomes that. So it is, notice here the denominator can be factored as x minus 1 times x plus 2. So what happened is that it became a constant over the first factor plus or minus a constant over the second factor. So that's what we expect always will happen. So we are going to write it as a over one factor plus b over the other factor. Now it doesn't matter whether you write a over x minus 1 plus b over x plus 1, or you write a over x plus 1 plus b over x minus 1. It won't matter. It will only change the sign, the values of a and b, but actually it will be the same thing. So the next step we do is we multiply by the LCM on both sides. And what is going to be the LCM here? If you may first write LCM is x minus 1 times x minus plus 1, or x squared minus 1, however you want to look at it. But it's better to have it in factored form. Now I wrote this step, so note here this step. You may skip it, but if you are not like expert in algebra, then please do this step, because it will help you understand what terms are cancelled and what are left. So the next thing we do in here, after simplifying, we get an equation with our coefficients to be determined and our the variable x, or x, our expressions with x. Okay, now our job is to find a and b. So there is a simpler way of finding the a and b, and that is what I'm using here. There is another way of doing it, which is also in this case not that hard, but in some problems it could be quite lengthy, and that is to expand, that I'm going to do over here. So expand the right hand side and collect the like terms. So you can write it as 1 equals ax plus a plus bx minus b. So notice here that ax and bx are like terms. So we can write it as 1 equals a x plus bx, or a plus b whole x. And then plus, then notice here that a minus b, a and b are like terms, so I can write it as combined a minus b. And now we can compare coefficients on both sides. So think of this as a linear polynomial and this polynomial. Then the term we will be comparing is the coefficient. So what is the coefficient of x on the right hand side? A plus b. And what is the coefficient of x on the left hand side? Because we don't see an x, so it means the coefficient is 0. So you can comparing coefficients. So that's another way of doing this, finding these constants or the coefficients a, b, by comparing coefficients. Okay, so in some books you will see this is the method being used. So how will you do that then? Well, you can write by comparing that a plus b is equal to 0, and then a minus b equals 1. Okay, why? Because a minus b is the constant here, and the constant on the left side is 1. And now you have two linear equations in a and b, so you can solve them by using your methods that you have learned. But here I have shown you like a quicker method to do that, and this is something, again, by practice and by a little insight you should be able to see. So if you notice, our equation is a1 equals a plus x plus 1 plus b into x minus 1. So we try to pick values of x such that at least few of our coefficients disappear. So for example, if I take x equal to 1, you will notice when I plug in x is equal to 1, this quantity is going to become 0, and b times 0 will go away. But we will have something here and we have something here, so which will give us a value for a. So that's what we do. We set x is equal to 1, so and plug in the equation, and we end up getting this, which gives us a is equal to 1/2. In the next step, we pick another value of x so that the other variable goes away, other coefficient goes away, and that is when we set x is equal to -1. So then you notice this from here that this term will vanish. So we end up getting 1 equals b times -2, and which gives us b equal -1/2. Now we can write our function or given expression as rational function, partial fractions. So notice here this quantity. So I'm replacing the values of a and b. So this is our partial fractions. And now we take this quantity and put it in the integral. So remember our integral was this. So now we use its new form that we found, and we can write it as 1/2 integral of 1 over x minus 1 dx minus 1/2 integral of 1 over x plus 1 dx, which are easy to integrate. So we end up getting 1/2 ln of absolute value of x minus 1 minus 1/2 ln of absolute value of x plus 1 plus c. Now we are using c here, and we can use c here because we haven't used c in anywhere else in the problem. But often you will see that if, for example, if we had another factor, so if our denominator looked like this, for example, then we will need a c, because now our partial fractions will be a over x plus b over x minus 1 plus c over x plus 1. So then if we are using c as one of the coefficients to be determined, then we shouldn't be putting a c here. So in that case, just to be on the safe side, what we can do is we can use a k instead of a c. Okay, so instead of a c, we can use a k as our constant of integration. So this is how we do partial fractions when we have linear factors in the denominator. In the next video, we will look at the second case.